Next, we're going to look at the exponentially weighted moving average control chart. This is another way to make a control chart for samples of parts or whatever you're doing. And it does similar things as a Q-sum chart. It takes into account the current sample, but also takes into account previous samples. Now, you can set a lambda we're going to have in our equation here such that the previous samples will be taken into account more or less. In other words, uh, the lambda value will determine whether the previous samples have a lot of influence on your uh, point you're plotting or if they have little influence. So here's the equation, going to be Zi equals lambda xi plus 1 minus lambda Zi minus 1, where lambda is between 0 and 1. Now, with this, I is the current sample that you're choosing, and the Zi's give you if you're going to plot. So, for example, if you're going to plot a point, say Zi here, let's say it's I is 5, then it's going to be lambda times x, the fifth sample, 1 minus lambda Z, the fourth sample. Notice this is going to be I minus 1. So this gives you an idea how much the previous uh, point will be in the now, I shouldn't call the Z the sample, but a weighted average of all the samples so far. And so again, if you want to have just the current sample taken into account, then you would make lambda equal to 1. So notice if you make lambda equal to 1, this 1 minus lambda here, this goes away. And so you're not taking into account anything that happened previously. And then if you make lambda small, then the previous sample would have much more weight. But again, DI takes into account current sample plus some influence by the previous samples. Now, the EWMA chart is good if you have to have like your sample size very small. Let's say if your sample size is only n equal 1. Now, n equal 1 would normally be a poor choice because the sample size is too small. It doesn't give you good indication. But sometimes maybe taking a sample would be expensive. Maybe you have to destroy the part when you test it. So you don't want to have a lot of waste. So you have to have the sample size small, or it's possible that you're even just making very few parts and you have to regularly check them. So this chart is good for that. In that case, this is the way we calculate it. And now starting value is usually going to be the process mean. In all these charts, we usually have a mean that we're shooting for. And so we're going to start like our Z naught because we're going to need a starting point for our equation. If you go back here, we need some Z naught to go over right over here because we're doing Z1. We have something over here. That's usually set that to be our sample, or actually going to be our target value. This is what we found in the past to be our normal value that we would like our parts to be made to. Now, again, once the process gets going, as I mentioned, the older sample means the less weight or influence they'll have. As I mentioned, they decline, actually they decline geometrically. For example, let's say if we set lambda equal to 0.1, the weight of the current sample mean is going to be 0.1 when you look back at our equation. The weight of the previous sample mean will be 0.1 times 1 minus 0.1 or 0.09. Weight of the one before that is going to be 0.1, 1 minus 0.1 squared or 0.81. So this would be the case again if lambda is small. Now, again, lambda, the smaller it is, the more influence the older samples are going to be. Now we can sort of plot these. Like for example, if we choose our lambda 0.1, in the current sample maybe 0.1, one before that to be less as we calculated there, then less. All of the previous ones have some influence you see like this. Now, on the other hand, if we make a lambda large, let's say we make a 0.3, again, the current sample is going to have a weight of 0.3. Previous one going to be, what that look like, about 0.21 perhaps. Then the previous one before that can be maybe 0.145, something like that. So you can see that the larger the lambda is, the less influence the previous ones have. And now, for a while, the previous ones still have a fair amount of influence. As time goes on, they'll decline quite a bit. And this is really true if lambda is large. For example, if lambda is 0.7, notice, excuse me, if we set lambda to be 0.7, the current sample is 0.7, that way to the current sample 0.7. The one before that is 0.21, I'd say, or 0.205. But notice the one before that drops all the way down to 0.06. The one before that drops all the way down to 0.02. So the larger the lambda is, the more dramatically the previous samples drop in their influence on our current point. Now, when we do the control limits for the EWMA chart are actually variable. And now we have the same form as we've had before the control charts. We have our process mean plus L times our standard deviation. Remember, L is usually the number of standard deviations, and we've usually used 3 for this. So the form is the same, except though this variance on the right or standard deviation, which takes the square root of it, is given by this much more complicated equation. So if we put our variance or standard deviation in our upper control limits or our lower control limits, we get something like this. So this becomes, again, a lot more complicated. I mean, it's not hard to calculate, but it just has more terms in it. And it's going to notice, again, the control limits are going to change for every point. And just like before, a point that plots outside the control limits indicates a shift in a mean. Now, as your samples, the number of samples gets large, as I gets very large, the control limits converge to this value here. So in other words, the control limits will change, but they'll eventually converge to these values here. So let's actually do a calculation here. So let's do an EWMA example. And let's say the mean, our target value we're shooting for is going to be 15. Our standard deviation is 2. And so we're going to, and like before, we're going to use L to be 3. Remember, 3 is, the general idea of 3 is the number of standard deviations. And lambda, in this case, we'll use a lambda of 0.2. Now we'll start by calculating our upper control limits and lower control limits. So again, calculate those. We'll calculate these for a couple of points. Remember, you actually don't need any sample points to calculate these upper and lower control limits. And so let's say again, that we're starting with our values, our mu naught or target value or overall sample refinement passes 15, standard deviation 2, lambda 0.2, L is 3. So if we're going to set up these equations, and we'll put the values right in, because these are going to be the same for every point. Put 15 here, 2 here, and set this up We can simplify it a little bit to get down to this for the upper control limit. So I just simplify a little bit so that'll be easier when we calculate of our control limit. Same thing for the lower control limit. We put in 15 for mu. We put in the standard deviation of 2 and L of 3. We get this. So we can use these two equations in bold here to calculate our upper control limit, the lower control limit. So let's start with our first point where I is equal to 1. All we have to do is substitute I of 1 into those two equations in bold that we had there. And so we get upper control limit 16.2, lower control limit 13.8. So we can put that on our chart, 16.2 and 13.8. And so for the next point, for the second point, I equal 2, go back to those equations in bold that we had and substitute I equal 2. Put I equal 2 here. And down here as well, we get 16.53, 13.46. We can plot those. Do that for a third point for I3. Again, in those equations in bold, just put 3 in here. We get 16.718, 13.282. We can plot that. So you can go ahead and go on and calculate all the upper control limits and lower control limits. But let's go back to calculating some z's. So as we said before, our target value is going to be 15, and that's going to be our starting value for z naught. Z naught is going to be 15. And according to the sample mean we have here, notice our first sample mean from our data is 14. That's going to be our x naught. Excuse me, that's going to be our x1. That'll be our x1 in our equation. So for our x1 be 14. Again, we just get that from our chart here. That's the data we've found. And so put that into equation again. Remember, our lambda was 0.2. Put 0.2 here. And then again, for your first point you can plot, I is going to be 1. And so if we use our equation, then this is going to be x1. And notice over here, of course, z is going to be I minus 1. That's going to be z naught. And now in this case, again, we're using our target up here. Z naught was 15. Now, from now on, we're just going to use the previous z value to calculate. So we put our values in, we get 14.8 for z1. And plot that, put that in your little chart here. Then do the second point. Second point from our chart was 17. Use the same equation. So I is now 2, so it's going to be 0.2 times x2, 1 minus 0.2. And then for z, again, it's I minus 1, so it's going to be 2 minus 1, which is 1. And again, we get our x2, again, from our chart, which was 17. That was the data we collected. And the z1, we get it from our previous value, z1. Notice that's up here. z1 was 14.8. Put that in for z2, we get 15.24. Plot that on your chart. And continue on. Our third point from our data was 16x, and that's going to be our x3. And so for z3, it's 0.2 x3 plus 1 minus 0.2 z2. Again, remember, the last term here is always I minus 1. So if I is 3, then it's going to be 3 minus 1 is 2. And then we get our z2 value that we calculated on the last step and use the 16 from our data. We get 15.392, like this. And then just continue on. You can go ahead and do the rest of the chart, do all the values, and plot plot them, and we get something like this. And if you plot these on an EWMA control chart, again, just plot the values I had here. Again, in the middle will be your Z values. They're in blue, and the upper control limit is in red. The lower control limit is in green. Once again, notice that the control limits change. But eventually you can see they sort of flatten out. If you go even farther, if we had more samples than 15, we would notice they would flatten out even more. But they do vary, especially at the beginning. And again, just like before, if any of those Z values, the points in the middle, if they'd gone either below the lower control limit or above the upper control limit, then our process would be considered out of control. It would indicate that we have a problem. And now, one thing to note, the Q-sum chart, which we had looked at previously, and the EWMA chart detects small shifts in the mean, but it does not detect large shifts, as quickly as the Shewhart chart. The Shewhart chart is the main control chart that we saw earlier in the course. So again, EWMA and the Q-sum chart, which you saw before, detects small shifts in the mean, but large shifts it detects, of course, but not as quickly as the Shewhart chart. So again, the Shewhart chart is good at quickly detecting large shifts in the mean, but not effective in detecting small shifts. In fact, sometimes you could have a small shift and not detect it at all in the Shewhart chart, or maybe it'd be a very, very long time before it would detect it. So the best strategy, if you have the resources, is to use the Q-sum chart or the Shewhart chart together. Again, the one to detect small shifts in the mean, the other to detect large shifts quickly, or use what we just saw now, the EWMA chart with the Shewhart chart, again, in order to detect small and large shifts in the mean.